record this first. Okay, good afternoon, ladies and gentlemen. Welcome back to the class. And so it has been a while that I have seen you all other than the test than last week because it's e-learning week. And so far we have been on track with, even though there's holidays and all that, we still are on track with our syllabus. So this week we are going to talk more into details on fire and explosions, which normally I'll spend 2 to 3 weeks on this chapter. That we won't actually go into details like the calculations of fires, calculations like at what conditions fire will start, at what conditions the fire will not start. But before we go into that, just to have a quick recap of what we have so far, allow me to share screen on this one. Just to, okay, so what you are seeing here is the assessment task. So you have done your test, and I will be giving back your test paper next Wednesday when we have class. And then your assignments are supposed to be due next week. But because since we have not covered our risk assessment, and looking at the class size, because we have a small class size where we will have sufficient time to do our presentation. So I'm thinking of extending the assignment to week 12 for all of you. Okay, so and then on week 13, we are going to have our presentation. So that you can present your case study according to your assignment report. Is that okay for you, or you prefer to stick to week 10? I hope that you have started to work on your assignments, yeah? Because right now, the assignment is ongoing, and then once you have done with your assignments, 15% is presentations based on the assignment that you have done. And of course, there's another 15% here on the certifications and reflections. So certifications and reflections have given you back the first one, which is 3%. And then the second one, which I opened up yesterday, I think, that is due this Saturday for the 12% or 9%. So you have submitted total of 12% of it. There will be one more certifications, which I'm going to give it to you sometimes in the next 2 weeks, within the next 2 weeks on the risk assessment, so that it covers up all the entire assignments for your to do hazards analysis, as well as hazard identifications, hazard analysis, as well as the risk assessment for your case study. Okay, so once you have the certifications and the reflections, you just need to submit as like what we did previously. There's only one more for you to do. So that will consist of 15%. So this 15%, if you notice that you actually go through 5 certification, so far you have done 4. So submissions of the certificates itself is 1 mark, and then the reflection is 2 marks, 2 mark each. So that's 15%, there are 5 for each one of you to do so. So if you have not done the 9 on hazards, the HIRA, the hazard identifications and risk assessment for this, the last week one, you may want to complete that because that consists of 9%. Remember to submit your certificates as well as your reflections. So for those who have submitted your reflection, I have not, to me on the first one, I have not taken a look at it. So I will take a look at it, and then I will just top up the marks for those who have submitted, yeah? So then that will basically sum out our coursework, our continuous assessment. Your final exams consist of 3 parts, MLO 1, 2, and 3. So that will be the simple like PSM, what's the 20% or mainly on the process system management. And then PLO, the MLO2, which mainly on the calculation. So one of the main calculations is actually this week and next week's class, actually today and tomorrow class on fire and explosion. So pay attention to it because that consists of 25 marks of your final exam. The other 25 marks come from your toxicology or industrial hygiene chapter, where you notice that our test has no calculation. So all the calculation is actually in your final exam. 50%, 50 marks out of it. So that calculation, that 25 marks will be on the TWA, TLV calculations. We talk about STEL and ceiling. And the other 25 marks is today's one and tomorrow's one, talking about the upper flammability limits, lower flammability limits, and then the explosions containment, as well as the what we call that, the damage from the explosions that we talked about, the overpressures and all that. Okay, so just a quick one. So in case you have not submit, yeah, so here's the 3 parts that you have to submit for week 6 to week 8, yeah, 9% of it. So I extend it to this Saturday, yeah, just to complete this, then you get your 9 marks here. So these marks are basically is to me is more like an attendance marks for you to attend these classes. And also you can add all these certifications to your CV, by the way, because these are international certificates. So once you have that, put that in your CV, trainings that you have been through, that international certificates that you have gone through from the safety module here. Okay, so allow me to go back to this one. Okay, so someone just joined. Okay, so today's we'll focus a lot on like what's fire, how does a fire starts and all that. Okay, so need to just get my iPad ready. Okay, so basically fires and explosions always come hand in hand. Sometimes fires start first, then followed by explosions, and sometimes explosions started first and followed by fire. So to understand the fire and explosions will help us to do first preventions. Second is to minimize the damage. Okay, combustions. Why do we need to study this? I believe all of you have done the test, the hydrogen test tube in the lab while you're in your high school. That 10 ml of hydrogen in the test tube where you put in an incense and then it go pop. That shows you a mini explosions by hydrogen gas. But right now, when it comes to chemical engineering plant, the chemical engineering design, we are designing chemical plants that is highly flammable. Some of the chemicals are highly explosive, like our hydrogen tank. So we have to understand how to make sure that all these safety feature has been taken into consideration. So the hazard here, as you can see from the screen, that 1 gallon of taurine can destroy a normal chemical lab in minutes and kill everyone in the area. And then organic solvents are the most common source of fires and explosions in this chemical industry. And to prevent it, we need to know the fire and explosion properties of the material, and then the nature of the process, as well as the procedures to reduce these fires, these hazards. Okay, so go back to basics. This is what we call the fire triangle. Fire can only start when you have a complete fire triangle. So the fire triangles means there's 3 parts in a fire to start. First, you need air, you need oxygen. But oxygen itself will not start a fire. And with oxygens, and when you have the fuel, means you have your fuel, your source of fire, okay? And that's where it helps to burn. But with fuels and with oxygen itself, it will not burn also. You need what we call an ignition source. It can be a spark, it can be a static charge, it can be high heat that causes it goes all the way up to auto-ignite temperatures, or it can be a flame nearby where it started the fire. So when one part, any part of this fire being taken away, like for example, oxygens here, the moment you remove oxygens, you inert the storage tank, Even though you have static charge and you have fuel, but without sufficient oxygen, the fire will not start. Okay, so that is why we have a upper fire flammability limit as well as a lower flammability limit. So without any of this, without oxygens, it will not start. No fuel, even you have an ignition source, the fire will not start. Or if you have these two, but that you eliminate all the potential ignition source, there won't be fire. One of the prime example is that when you are in a petrol station pumping gas, yeah, most of the time fire won't happen because the fuel itself, the fumes, because the fuel when it is in liquid form, it will not burn as much. But when it started to becomes in gas form, that's where the fires actually burn. So when you pump petrol, if you notice that there are a few things you are not supposed to do when you are pumping your petrol. First is do not use your handphone. Do not do a text message or do not make a call while you're pumping petrol next to your car. Because that is the ignition source. Because every signal that we send out, it has a potential to cause a static charge, okay? A static spark. And also, you are not supposed to smoke at this area because those are the ignition source. So if you really need to make a phone call or anything, do it inside your car or do it away from that stations where is next to the pumping hose. Okay, so that's one part. In the past, we would tell people not to have handphone at all because the previous generations of handphones, the magnetic fields and all that are huge. The signals are too strong. But nowadays, with the technology advancements, it's becoming safer and safer, but still we want to eliminate all the potentials sparks. Okay? So the difference between fire and explosion is that fire actually burns slow compared to explosion. Explosion is where the moment it started, what causes the damage is not that fire, it's not the burning, but the overpressure. It caused by the pressure, okay? So fire release energy slowly, explosion release energy in an instant. Okay, so fire can result from an explosions and explosions can result from fire. So they are like, they goes hand in hand very often. So fire is a chemical reactions between substance and oxidants that release the energy. And ignitions, okay, some things that I want to bring to your attention is the auto ignite temperature, which at certain temperature where when the substance has enough energy to start a fire, you or at AIT, right, auto ignite temperature, you don't need a spark to start a fire. The fuel itself has enough energy to burn by itself. Okay. So flash point of a liquid is the lowest temperature where it starts to give off vapor to form the ignitable mixture with air. Okay, so you have seen in your SDS, the ones that we already look at. If let's say you go to the fire's properties, it will tell you the flash point, and some substance, if let's say they have the AIT, they will also tell you what is the AIT temperature. Please pay attention to that because I have seen students when it comes to their capstone design, means your group projects 1 and 2, because for those chemical engineering students, most of you are taking this module together with your process plant design economics. So in next semester, you will start to design a chemical plant that's given to you. So I have seen students where they wanted to run their reaction at, for example, 400 degrees Celsius. Okay, for methanol. This is one of the case that I saw in previous semester where they one of their reactants is methanol, and they run that the reactions temperature, the reactor at 400 degrees Celsius, where the auto ignite temperature for methanol, if I'm not mistaken, is 415 degrees Celsius. So you're basically running at a very high risk that your reactor tank can start a fire anytime. because you're running at such high temperature. And sometimes when we control, we have a plus minus 15% or 5% to 10% of that fluctuations in terms of temperature. And with that, automatically you shoot across above the auto-ignite temperature. So whenever you want to design a chemical plant at high temperature, always double confirm what is your AIT. Okay. So hold on, give me a minute, because I think I hear my son's. Okay, so there are a lots of different type of explosions. When we say general explosions, it talks about chemical reactions explosions. But there are also things like mechanical explosion due to the pressure buildup. And also we have something called the confined explosions where it's within the building or within the what we call the blast wall. And also the boiling liquid expansion vapor explosion is a very long, lengthy words explosions that in general we call it BLEEF. Or dust explosions, which later we have videos talking about what is dust explosion. Even finds dust, when you accumulate enough of them, it has a potential to cause explosion. And what shortwave and deflagrations and detonations, etc. So these are just basic fire and explosions definitions. Okay, so let's take a look at this chemical reactions explosions that we had here. Just give me a moment to reshare the screen here. Okay, so do let me know if you can hear or if you can or cannot hear the
On December 19, 2007, a powerful explosion and fire occurred at T2 Laboratories, a small chemical producer in Jacksonville, Florida. The blast killed and injured workers, destroyed T2 Laboratories, and extensively damaged 4 nearby businesses. Windows blew into offices, striking workers with flying glass.
The explosion at T2 Laboratories is one of several accidents that the CSB has investigated caused by runaway chemical reactions. Accidents resulting from reactive hazards occur too frequently and often have serious consequences.
Behind me on this concrete pad, there used to stand a structure some 50 feet high that had a reactor vessel in it, in which the company that operated here, T2 Laboratories Incorporated, manufactured a chemical known as methylcyclopentadienyl manganese tricarbonyl, or MCMT for short. The entire structure and reactor vessel were blown away in the explosion.
T2 produced MCMT, a gasoline additive, in batches using a 2,500-gallon reactor. An operator controlled the process with a computerized system in a nearby control room. In the first step, liquid chemicals and sodium metal were loaded into the reactor, heated, and then mixed with an agitator. The reaction produced hydrogen, which was vented to the atmosphere. In normal operations, when the temperature reached 300 degrees Fahrenheit, the operator would turn off the heating system. But because this reaction was exothermic, or heat-producing, the temperature inside the reactor would continue to rise. At 360 degrees, operators would begin to periodically fill the reactor's cooling jacket with water. As the water boiled, heat was removed, controlling the temperature. However, on the day of the accident, the CSB found that the operator tried to cool the reactor as usual, but the cooling system likely malfunctioned, perhaps due to a blockage in the water supply piping or a valve failure. The temperature and pressure inside the reactor began to rise uncontrollably in a runaway chemical reaction. T2's co-owners returned to the plant after a worker called to report the cooling problem. While one owner searched for the plant mechanic, the other went to the control room. Concerned about a possible fire, he warned employees to move away from the reactor. Inside the reactor, the pressure was still increasing, reaching 400 pounds per square inch and bursting the rupture disc. Witnesses heard a sound like a jet engine as high-pressure gas began to vent from the reactor. But it was too late. Within 10 seconds, there was a massive explosion, equivalent to about 1,400 pounds of TNT. The blast damaged buildings over 1,500 feet away. Debris rocketed up to a mile. The co-owner and the operator in the control room were killed. 2 operators further away died from flying debris. 32 other people were injured, including 28 at nearby businesses.
This facility housed multiple types of chemicals. That was a kind of a mass storage of everything you can think of, and it was all mixed together and it was all burning together. And for our perspective from the hazardous material side, it makes kind of a worst case scenario.
Damage from the explosion was so severe, 4 nearby buildings were condemned.
My office personnel heard a whistling sound in the area, and as they looked out the window, they saw an orange glow, which was the blast coming off of the explosion, and it came to our offices and it blew in all the windows in our office trailers. Immediately it was a shock or a surprise, and then all of us were shaken afterward.
In 2002, the CSB completed a study on reactive chemical hazards. The study identified 167 serious accidents involving uncontrolled chemical reactions between 1980 and 2001, causing 108 deaths and hundreds of millions of dollars in property damage.
When mixing chemicals that have an exothermic reaction, you need to be aware of the amount of energy that could be released by the reaction to prevent vessels from bursting like the one that happened here.
T2 developed its MCMT process using a 1-liter reactor. The company then scaled up the process directly to full production volume in the 2,500-gallon reactor. After 41 batches, T2 increased the batch size further by 1/3. As the scale of the reaction increased, effective cooling became ever more difficult. During 175 production runs making MCMT, T2 periodically experienced problems, such as unexpected temperature increases, but the company never fully investigated the causes. And T2 had only equipped the reactor with a simple cooling system using city water. When the system malfunctioned, there was no backup cooling immediately available to control the reaction.
The most important thing to managing reactive chemistry hazards is that you have to have a thorough and complete understanding of your chemistry under design conditions and also under all foreseeable abnormal conditions.
The CSB has noted that to prevent reactive chemical accidents, companies should identify and thoroughly evaluate reactive hazards in their processes, implement appropriate emergency pressure relief systems and other design safeguards, develop effective operating procedures and training programs, and carefully manage any changes to existing processes, and plan for possible accidents, including evacuation drills and emergency response exercises. Although T2's owners had undergraduate degrees in chemistry and chemical engineering and experience in the chemical industry, neither had been trained on how to recognize or control reactive hazards.
A large portion of the incidents have occurred because the people who are actually running the process were not aware either of the existence of the reactive chemistry hazard or of the potential magnitude of the consequences associated with that chemical reaction hazard. So a lot of the problem, I think, is education and awareness.
The board noted that multiple sources of information are available on how to control reactive hazards, including publications from the Center for Chemical Process Safety, the Design Institute for Emergency Relief Systems, and the UK Health and Safety Executive. Following the T2 investigation, the CSB recommended that the American Institute of Chemical Engineers work to incorporate education about reactive hazards into college-level chemical engineering curricula.
Reactive chemical hazards continue to be a too frequent cause of chemical accidents. Improved industry practices and increased education will help prevent these tragedies. Thank you for watching this.
Okay, so basically, if you notice this one, we have covered some of the chapters here. They did use the relief system. Remember, we talked about it in our fourth chapters or our fourth classes, where the relief design was there. However, it was actually not sufficient. But the biggest issue here is actually go back to our first class when we talk about the change management. One of the elements for process safety management is that one of the elements talk about change management. Here, the change management basically is where the company designed the reactions using a 1 gallons reactor. However, they actually increase the capacity. While increasing capacity without re-looking at the reactor itself, without re-looking at the cooling system, the cooling capacities, etc. So when you do your plant design in the future, be it for your next semester, for the students level, we call it the academic level of plant design, or when you go out and start working where you are asked to expand or increase capacity for your production line. These are the things, if you're working in a chemical or petrochemical plant, these are the things that you need to take notes on. It's not to say, oh, I have a big volume of the reactors. Yes, I can do that. It also comes into, yes, the reactor's volume is there because when you design, you want that. You want it to be maybe 60% liquid, 40% in gas form, or but at the same time, you need to restudy and recalculate the liquid flow, the cooling system flow rates, and all that. And also, some companies, they have decided, okay, right now when they decided to use coolant. So coolant has a better cooling efficiencies and all that. But over the time where they say, okay, now we need to do a cost cutting. These coolants are expensive. Let's change it to city water cooling. So a lot of time people just, the moment they want to change, they forgot about safety. They will just say, okay, let's change it. Okay, so that's where detailed study and redesigning, recalculations are needed. This go back to your semester 2 modules, thermodynamic and heat transfer. So you have to recalculate all that transfer and also your fluid mechanics. Yeah, you have to recalculate all that fluid flows as well as the energy exchange between the tubings, between the piping and all that. Before, as engineers, that we can say, oh, we signed off and say, yes, this can be done. Okay, so the one of the take home from this video is that when we do a capacity increase, whenever we have a so-called process change, the design has to be restudied. Okay, so this is on chemical explosion. The next video we have, I'm just going to go directly into that, is about dust explosion. So dust explosion, these incidents happened back then, if I'm not mistaken. Let me take a look. It was in 2008, I think. Yes, 2008, where it happens in the sugar manufacturing, yeah, one of the very famous sugar manufacturings in the world. So this is what happened.
At 7:15 p.m. on February 7, 2008, a series of violent sugar dust explosions devastated the Imperial Sugar Refinery in Port Wentworth, Georgia, just outside Savannah. Explosions raced through the buildings, fueled by accumulations of combustible sugar dust and sugar that had spilled from equipment. Thick concrete floors heaved up, and brick walls were blown into stairwells and work areas, blocking many exit routes. Fires spread rapidly. 8 workers died at the scene. 6 more died later at a regional burn center. Dozens of others were injured. The plant's massive sugar packing buildings were a total loss.
The accident at Imperial Sugar was the deadliest industrial dust explosion in the United States in decades. It highlights the extremely serious nature of combustible dust hazards.
There were significant accumulations of sugar dust and spilled granulated sugar on surfaces throughout this facility. Conditions were set for a catastrophic accident.
Imperial Sugar's sprawling Port Wentworth complex began operations in 1917 and grew to become one of the largest sugar refining and packaging facilities in the U.S. Granulated sugar from the refinery was stored in 3 100-foot-tall silos and then conveyed into packing buildings where it was packaged for distribution. Granulated sugar was also converted into specialty products, such as brown sugar and powdered sugar. Sugar was transported by a complex system of bucket elevators, screw conveyors, and conveyor belts. During this process, sugar spilled onto floors throughout the work area. In places, the spilled sugar was many inches deep. This sugar also contained fine particles which became airborne. In addition, hammer mills were used to crush the granulated sugar into powdered sugar, creating even more dust. The machines were connected to a dust collection system, but it was undersized and in disrepair. And it was not connected to the bucket elevators and conveyors. Significant amounts of sugar dust escaped into the work areas. Workers routinely used compressed air to clean packaging machines, further dispersing sugar dust throughout the buildings. Over time, large amounts of dust accumulated on elevated, hard-to-clean surfaces, such as ducts, beams, and light fixtures. These surfaces were not cleaned often enough to always keep the dust below hazardous levels. In the tunnel beneath the sugar silos, granulated sugar flowed through chutes onto a long steel conveyor belt. From time to time, clumps of sugar would become stuck in one of the chutes, blocking the flow of sugar on the belt, spilling sugar onto the floor and releasing dust into the tunnel. But the tunnel was large and ventilated, so this airborne dust did not build up to explosive concentrations. However, in 2007, the company enclosed the conveyor belt with stainless steel panels to protect the sugar from possible contamination. The enclosure was not equipped with a dust collection system. As a consequence, sugar dust would now be trapped inside this enclosure. On February 7, 2008, clumps of sugar were found blocking one of the discharge chutes. Sugar from the adjacent silo likely spilled off the moving belt. Dust likely accumulated to an explosive concentration inside the enclosure. At about 7:15 p.m., the sugar dust contacted a nearby ignition source, likely an overheated bearing, and exploded. This primary explosion blew apart the enclosure and vented into the packing building. Accumulated sugar was lofted and ignited by the advancing fireballs. The dust clouds fueled a chain reaction of secondary explosions, which swept through the buildings. Concrete floors buckled, releasing tons of granulated and powdered sugar into the flames. Emergency evacuation drills had not been conducted. and the explosions had cut the power to much of the interior lighting. In the maze of darkened and damaged stairwells and passageways, workers desperately tried to flee the growing inferno. The CSB found that correspondence dating back to the late 1950s showed that plant managers in Port Wentworth were aware of the explosive nature of sugar dust and the danger of dust accumulations. As far back as 1961, a memo described a sugar dust explosion that heavily damaged the powdered sugar mill room.
Despite the long-standing awareness of the explosive nature of sugar dust, not enough was done to manage the hazard.
In 2006, the CSB issued a study of combustible dust, which called on OSHA to establish a comprehensive combustible dust standard based on the current standards of the National Fire Protection Association, or NFPA. In October 2007, OSHA began implementing a new national emphasis program to increase the enforcement of existing regulations related to combustible dust.
Imperial Sugar learned of the OSHA Combustible Dust National Emphasis Program 4 months before the devastating explosion at Port Wentworth. But management did not act effectively to control the serious dust problem in the packing buildings.
Less than 2 months before the disaster, an internal inspection showed that many tons of sugar were still regularly spilling onto the floors. This provided much of the fuel for the massive secondary explosions and fires. The CSB found that over the years, the Port Wentworth facility periodically experienced small fires fueled by spilled sugar and accumulated dust on equipment. But none resulted in a sugar dust explosion that propagated through the plant. Investigators said that decades of operating without a catastrophic explosion may have lulled managers into complacency. In its report, the CSB issued the following recommendations to the Imperial Sugar Company. Apply NFPA standards to the design and operation of the rebuilt Port Wentworth facility. Develop and implement comprehensive combustible dust control, housekeeping, and training programs. Improve emergency evacuation policies and procedures.
Companies can go a long way to control combustible dust within their own facilities by following the existing recommendations of the National Fire Protection Association. But it is also time for a comprehensive federal standard on combustible dust.
In April 2009, OSHA announced plans to begin rulemaking on a combustible dust standard for general industry. In its final report on the Imperial Sugar accident, the CSB recommended that OSHA move forward expeditiously with the new standard.
Without regulation, enforcement, and education, workers will continue to be at risk from catastrophic dust explosions.
For further information, please visit csb.gov.
So now we have viewed the first explosions that caused by chemical runaway system, and the second one was caused by the dust explosion. So there is a question here: where is the source of fire? So what happened is that the fuel is basically all the combustible dust, because fine dust, right, that is made of organic metals actually can burn. And so when they have, remember that's halfway through the videos, they talk about, they talk about the accumulations of this one where they have this blockage. So when they put up the tunnels to contain, to reduce contamination, okay, what happened is that they pile up the tunnels are over here. The flammable limits of dust inside this tunnel. Okay, so to the level of explosive. So the moments they have that clump in there, let's see, the moments they have this clump where they suspect it actually causes, because overheats of belt that causes the sparks to happen, because these are all conveyor belts. So when conveyor belts, as we know, if let's say they continue to run, it start to generate heat, and sometimes sparks may just happen. Okay, so that's where it started, the whole explosion. It's not started by the fire, but it started as an explosion. Okay, so any questions regarding this too? On the what we call the fire and explosions, the explosions caused by chemical runaway, and the other one is caused by the what we call the okay, let's see if we are share device audio. Okay, let's go back to my PowerPoint. Okay, so just now we have viewed this chemical reaction explosions, and then followed by the dust explosion. So because a lot of us always thought that only chemicals can start fire, but dust explosion does happen, especially in all these like the food processing plants, like any flowers plants, like cornflowers, or any processing plants that has fine particles as this risk. Okay. So the next one, we're going to talk a little bit more about what is deflagrations versus what is detonation. Deflagrations is where the burning is a fire, where then when we add substance that makes the process suddenly burst out, like that is faster than combustions but slower than this detonation. So a good example given here is that adding water to burning oil that can cause a mushroom-like fires. Okay, so that is where the water droplets get into vaporized because of the high heat, and then that carries the fume all the way up. That's what we call deflagration. Detonations basically is a shock wave caused by the explosion greater than the speed of sound. Okay, deflagration is lower than the speed of sound. Detonation is faster. It travels faster than the speed of sound. So as when we look back at these two videos, right, the moments the explosion happens, it was like detonates a bomb. Okay, it just happens, and it thinks there's no time for people to react. When there is a fire, there's time for people to evacuate. But when the explosion hits, the moments at that point of explosions, there's no way that people can run. Okay, that is why the explosions-proof wall are very important wherever we design a plant that has the potentials of explosions. Okay, so when later on we are going to talk about flammability limits. What you're looking at is just the official setup of the flammable study of liquid and vapor. Okay, we are not going to go detail into it. This is more like a introductions on how do people get the flammable limit on the upper flammability limit and the lower flammability limit. Okay, so this is mainly done by OSHA, or the EPA, the Environmental Protection Agency. So they have combined together, they have joined hands to study all the chemicals of the flammability limit. Okay, so basically they talk about the vapor mixture, and that it depends on also it actually varies, it actually increase upon temperature as well as pressure. Okay, so this is a simple graph. I believe some of you may have seen something similar but different. Okay, in your CETS, Chemical Engineering Thermodynamics module, we talks about all the three-phase study. Okay, over here, we look at the flammability study. Okay, where anything between this curve, okay, over here is flammable. Okay, anything that is outside, let me change a different color. Over here or over here, either you do not have sufficient, if let's say over here is that you do not have sufficient oxygen presence in the environments to cause it to burn. Over here is not enough fuel. Yeah, this is mainly not enough O2. So, but however, anything in between, oops, sorry. Anything in between this area, you will have enough O2, you have enough fuel, and the moments you have sparks or the ignition source, the fire will happen, okay? However, if you are in this region, allow me to use a different color. This is where you don't even need sparks. It will start to burn, okay? So these are the regions that we talk about, the octo-ignitions region. Okay, so this is being calculated. So whenever we have this data, okay, let me to go to our flammability, our data booklet. So what you're looking at is the booklets that we always refer to. So formulas are all given in here for fire and explosion. So let's go to the data. Okay, later on we are going to talk about all this data here, but let's go to the flammable limits data here that you can see. So apparently I have difficulties. Okay, so this is where all the data you can see methanes, ethane, propane, and all these flammable chemicals, they have tested what are the levels. So you have a lower flammability limit and upper flammability limits in the air. We are not concentrating on the liquid form, but we are concentrating the percentage, volume percent of the fuel in the air because that's the ones that actually is burning. Okay, so in order for us to calculate, because in a chemical lab, sometimes we have multiple chemicals or in a workplace. So to calculate the vapor mixture, so these are the chemicals, what we call the formulas to use, okay? So LFL mixture is 1 over Y is the component, is the mole fractions of this on a combustible basis over the flammable, the lower or upper flammable limit of each of the components. So these are just the calculation part. Next week, we are going to do a lot of LFL and UFL calculations on Wednesday during our tutorial slots. So today is mainly on theory on the fire and explosions. Then next week, we are going to talk about the calculations. So do not miss the class next week, yeah? So that is the, this calculations is based at 25 degrees Celsius, which is what we call the standard room temperature, yeah? So all this data that you see in here is actually done due at 25 degrees Celsius at room temperature. Okay, however, just now I did mention that the flammability limit actually increase or changes, okay, according to temperature and pressure. So when we have an increase of temperature, okay, so we have to make sure this temperature is in the degrees Celsius. And also this is the net heat of combustions in kilocalsins per mole. So where do you get this data? Again, come back to this one. However, you have to note one thing here is that this is in kilojoule per mole. Yeah, we need to convert this to kilocalsium per mole. How do we do that calculations? That is why I have given you all the unit conversions table right before this one. So over here, you can actually calculate in terms of joule to calorie. Okay, you just use the conversion. So 1 joule is equal to 0.239 calorie. And so you just change it. So you just have to times this one times 0.239 and you get the level. So question is, do we use the lower or upper level? For calculations here, most of the time we'll use the lower level. Okay, so why do we have two levels here? Because this is mainly because the study was done on two different scales. So to study what is the arrangement between A to B. So A is calculated by chemical properties by Carl, and B actually is the studies done by this Suzuki. Okay, so there are two different studies. One was done 1999 and the other one is done 1994. So in normal calculations, we will just use the lower limit. However, if you want, you can use any values between here. But I would say don't give me a middle value. Just either you use here or you use this value. But most of the time, our calculation based on the lower level. Okay? Any questions so far? Okay, so this one, that's where we talk about the kilocalsins. Remember, you have to convert, yeah, because table give kilojoule per mole. So you make sure you need to convert it. Okay. And then this is on temperature change. This is on pressure change. Pressure change will not affect the lower flammable limit, but it will actually increase the upper flammability limit. So that ones we will take a look during the tutorials when we have calculations. So today we are not going to do on calculation. We are just going to talk about theory today. Okay, calculations will be on next week tutorial. So any questions so far? Okay, so if let's say given the data and you can't find this flammability limit in, in any of here, okay, so we have most of the substance here, but then you realize, oh, I actually don't have a data in this, shows in this table. So how, if let's say your substance is not fine, what we will do is to use go back to basic, use the stoichiometries of combustions of fuel to calculate. So this is the generic formulas there. This is your fuel formulas. So you have to realize one thing, fuels will always have either carbon or hydrogens. If it's only oxygens, we don't worry about that. And also we don't calculate other things like nitrogens, etc. So it's only hydrocarbon. So you have H, you have C. So once you have any combinations of H and C, H or C, because hydrogen itself will burn also, you can use this formula to estimate what is your upper flammability limits and lower flammability limits. So this is the generic calculation. So if you have like for example methanol, where you have C1 CHOH, so you have C, 1 C, 2 H, and 1 O. Then you just do the balance of these equations, you get this value. Okay, so your Z value is calculated by this whole thing. So you know your chemistry, right? Okay, so with that, then what you need to do is when you calculate your upper flammability limits and your lower flammability limits, you just need to substitute your M, X, and Y from this one, your chemical here, to estimate your upper and lower flammability limit. It's as simple as that. Okay. So this is just if let's say your chemicals components are not found in the tables that is given, then we will use the basic, the generic flammability limits calculations. How does this calculation come about? It's all done by the scientists as well as the mathematicians, because they have done lots of tests. And with that, then they come up with what we call the mathematical modelings that fits to most, like most of the time we will say 99% confidence rate, that wherever you plot in this data, it will actually 99% fit to the experimental data. Okay, so what you need to do is to know what is your chemical components here, this one, and substitutes in here, you get your upper and lower flammability limit. Any questions so far? So this is mainly to assist you when coming to next semester where you need to do your stoichiometric calculations for your reaction. Okay, and then later on you want to calculate when it comes to CEGP2, when it comes to safety side, you need to recalculate what is your flammability limit, and you want to see how much chemical can you store, and what are the prevention methods from any of these fire or explosions from happening. Okay, so that will be in your CEGP2. So in order for you to understand, okay, how do I do all these calculations? The formulas are here. Okay, any questions? Okay, so if no, that we actually cover the calculations on the upper and lower flammability limit, but the actual calculation we'll only do it in class together during the tutorial. That will actually helps you to say, okay, how do I use all this data? Now today's we only focus on theory. Yeah, so explosion behavior depends a lot on these parameters. What is the temperatures? What is the pressures? What is your compositions of your explosive material? And also your natures of your ignition source, the type, the energy, and the durations. And of course, the surrounding, be it a confined or unconfined situation. And also, because that will help you to decide, do you want to design a confined manufacturing plant, or you want to design an unconfined manufacturing plant? The ones that we actually look at the dust explosions, it was supposed to be a confined manufacturing plant because it is inside a building. So if, let's say, they build their building correctly, with all this anti-explosive wall, or we call it the blast wall, the damage will be way smaller towards people. But towards the manufacturing itself, when explosion happens, whatever equipment or unit operations within that compound is all gone. Okay. And also the amount of the combustible material, as you can see from both, right, their amounts is huge. Because like the first one, the chemical explosions, what happened is that they basically increase the capacity of that reactors, yeah, without resizing it and without restudying it. And the second one is that they have this 300 feet silo of storage, and that whole plant is full of the dust, the explosive dust. Okay, the time and also the rate of combustible material is released. So these are the things that we need to study. And the natures of explosion. There are a few different types of explosions here. Yeah, one is something that we want to really be careful of is the vapor cloud explosion. Okay, so vapor cloud explosion is like where it has a sudden release of huge amount of flammable vapor. Okay, and it dispersions is mixing with air, and it results in the vapor cloud. A very good example of vapor cloud explosions lately is where, if I'm not sure any of you are still remember, during pandemic, we have one Beirut port. They have this fertilizer explosion, yeah. And that actually is one of the, what we call the vapor cloud explosion, because it's where the chemical reactions, there is fire at the site, and then it's stored next to, and the fire happens next to the storage of this fertilizer. And fertilizers are mainly a mix of two types of chemical components, nitrates, and also mainly is the nitrates-based fertilizer. So when it comes with heat, right, it actually, the molecule wants to break into two different types of vapor chemical. One is ammonium gas, one is nitric oxide. So in the Beirut explosions, which I didn't prepare the videos today, in the Beirut explosions, what happened is when the fire started, the chemicals were basically boiling. It was being cooked in that high temperature. So the chemicals start to wanting to break free from each other. So when they have enough energy, it just break free. And with that, it explodes spontaneously and causes the vapor cloud explosions that looks like what we call the mushroom explosion. Okay. So believe the boiling liquid expanding vapor explosion is where, okay, vapor cloud explosions is mainly the huge amount, releasing of huge amounts of flammable vapor. And believe is where when we have a tank, when the tank itself being heated up, it's very similar to the first one, yet different. This is mainly on the liquid itself, but the liquid has been boiled and turned into gases. And the explosions happen because of mechanical failure, because the tank cannot take it anymore. Hold on, give me a minute. Sorry for the interruption. Okay, so believe basically is like a boiling of pressure vessels until all the liquid has started to break the mechanical design of the vessel. I have one video here that I can actually show it to you how it happens. Okay, hold on. I need to reshare the screen. Okay, so yes. Okay.
When a tank is exposed to sustained heat, such as from a fire, the liquid within the tank is forced to boil or vaporize, resulting in increased pressure in the tank. To prevent overstressing the tank, the relief device activates, venting the excess pressure. As pressure decreases in the tank, the valve begins to close. With continued heating,
So that in case you are not aware, just know there is a relief valve there, but that is a spring loaded. So what happened is that when the pressures go up, the spring loaded relief kick in, that we release some of the pressures and it continue to burn. And then the moments the pressures go back to the what we call it the designs pressure, it just sit back. Yeah, so that's where, if let's say in case any of you missed out the relief, let me just repeat.
as pressure decreases in the tank, the valve begins to close. With continued heating, pressure again builds, causing the relief valve to reopen. Where flames impinge on the tank below the liquid level, the liquid absorbs the heat, allowing the tank metal to remain at a safe temperature. With continued relief valve operation, the liquid level drops, exposing a greater area of the tank to the effects of heating. With the flames impinging on the vapor space of the tank, the temperature of the tank metal, uncooled by liquid, rises. At some point, due to the vapor pressure from within, the tank metal begins to weaken, stretch, and eventually tear. As the tank comes apart, large quantities of both liquid and vapor are released in a powerful explosion. The heat radiated is sufficient to ignite combustibles and cause burns great distances from the explosion. Tank sections containing rapidly igniting fuel can become flying missiles, traveling great distances, causing secondary fires and other damage. It all happens quickly and with little warning.
So what you're viewing here is the experiments that demonstrations on BLEEF. Yeah, some they call it Bleeville or any however you pronounce it. So in these explosions, there are two component. One is the build-up of the conversions of the liquid into gas phase. The other one is the weakening of the vessel's mechanical property because of the temperature. So there are two failures in here that causes this kind of explosion. Okay, so allow me to just go back to our okay, so any questions on this one? So explosions, normally when we talk about explosions, we estimate what is the blast damage from overpressure. So after all this combustible material is consumed, the reaction is terminated, but the pressures continues to go outwards motion. So the damage from explosion is actually more damaging than the fire. If let's say there's a plant, as long as the fuels get burned, it contained within the plant. But explosions, as you can see, things are starting to move all over the places where it actually has a larger damaging area. Okay, so it's the blast wave that causes most of the damage. It's not so much of the fire. So if let's say you recall the first explosions, the chemical explosions, those houses around it was being damaged by all the flying debris. Okay, so these are another two explosions in the chemical plant, which I think what I will do is I will upload this one in my times. Later on, you all can view on this different fire explosion. All these are caused by different type of chemical. The first one talk about the polymer, what we call it, they call it popcorn polymer, means basically is the polymerization process in the chemical. And then the second one talks about the pressure vessel. Okay, what I wanted to introduce you is that when we talk about the damage, right, the blast damage, we often look at the pressures versus what is being damaged around it. So allow me to just draw in this. So when a fire happens in the middle, okay, so assuming this is round, yeah. So as it goes, it actually goes, the explosions happens in all area, top, bottoms, and the side. Okay, so what we need to do is we want to know what is the damage, okay, within certain distance from the blast zone towards this area, or if let's say there are people somewhere here, what's the damage from the blast zone to here? So this is what we call the R, the distance. Okay, this helps us to design how much can we store in a chemical plant, or what is the safe distance that your chemical plant, because later on when you do your plant design, the first chapters you need to study is your feasibility study, that you need to do a site locations. Yeah, means you need to decide where do you want to put your chemical plant. So of course, at that point of time, you're just studying, okay, I want to build it here. Perhaps I want to build it in Kuantan, or I want to build it in Klang Valley, or I want to build it in Sabah, Sarawak, and all that. So you find a place to build your plant, okay? But later on, when it comes to the safety chapter, you have to revisit your site selections plan to see, okay, nearby, is there any housing area nearby, and is that within the safe distance? Okay, so as you can see, when we talk about safe distance, there is this what we call a safe distance for us to design is at the pressures 2.07 kilopascal, or at if let's say you use the PSIG gauge, it will be 0.3. So with this, when we say safe distance, is where 95% of no serious damage below this value. Okay, it's a projectile limit, some damage to the house ceiling, but it will not cause too much of the injuries and all that. It's that's what we call safe distance, because we can't design it at zero. When we design things at zero, right, everything cannot run. So that's where we always want to put a gauge. So what is the minimums that we can go to? Remember, even in our chapters on toxicology, even the TWA, or when we talk about the Probit equations, we say 1% death rate, 0%, we use that the lowest value, the 2.66, because 2.67 is 1%. So we assume 2.66 and below will be 0. That's where this the similar situations where we call this a safe distance. Okay, so anything above this level, above this threshold, it will have a higher damage. Okay, so this is where the tables that we will refer to during your calculation. So again, let's see if I have any sample calculations to do. No, it's just introductions of the formulas. So whatever substance we have, yeah, all this chemical, what we will do is we will convert them into TNT equivalents. Yeah, so TNT is the what we call the standard what we call that, the standard language that we use to know that what is the blast damage. Okay, so if let's say you remember just now the two dust explosion as well as the chemical explosions, they actually talks about equivalence to how many tons of TNT being released. Okay, so in the calculations for fire in explosions, we always convert our chemicals to equivalence TNT by using this formula. So TNT formulations is this one. Okay, so the equivalence of mass of TNT is the empirical explosion efficiency. Most of the time, it will be given, or excuse me, you can find them in some literatures for different chemicals. They have a different empirical explosion efficiency. Like for example, fertilizers is about 0.4. Okay, so and then the energy of explosions of flammable gas. Against this one, we use the delta HC in terms of the combustions equations, combustions data, which again come back to here, which is the heat of combustions here, the kilojoule per mole. Yeah, again, you can use the lower or upper data here. Okay, and then of course we talk about the energy of explosions here. TNT is 4686 kilojoule per kg. That is the standards that we use. Okay, so later on when we want to do the calculations, which we are going to do it during our tutorial again, we are going to do a lot of calculations during the tutorial next week, that we will calculate what is the distance, yeah, and use the graph here to study what is your scale distance and the scale over pressure. To study back what is your ambience, what is your scale over pressures here, the peak side on over pressure, in order for us to study what is the potential damage. Okay, so let's not worry about all these charts. We will focus on them next week. Okay, so more examples to come in the tutorial. So any questions about our class today? So it looks like we have a quite short class today, because since I'm not going through all the calculations in this class. So make sure you understand the theory, like how it happens and why, like how things happens and what sort of difference fire and explosions. And next week tutorial, because tomorrow I intend to use the class to talk about prevention. And then next week when we have class, or if let's say you want, we can actually convert our tomorrow class into tutorial also for fire explosions. Then next week we will use the tutorial class to talk about the prevention. We can do that also. In fact, I prefer online classes like this because we can record it and then I can post it later to the class so that you can revise, because I noticed our tutorial class has no recording in the classroom. So for the calculations part, I would prefer to record it so that it's easier for you all to do revisions later. So in that case, I think I'll do a swap again. Tomorrow we will do tutorial, okay? And it will be online tutorial so that we can do the recording. Then I can post the tutorial sessions online in my times for all of you. Is that all right? In that case, then I'll see you tomorrow, yeah, for our tutorials on this one, fire and explosions. Then next week class, do you prefer an online class like this, or do you prefer a face-to-face class in the classroom? I leave it to you all. If you all want a physical class on next week, we can do that also. But that will be Wednesday will be a lecture class. We are going to swap it because it's just weird to have tutorial first then lecture. So Wednesday we will have lecture class on okay, so a lot of no attendance because all 7 of you are here. We have 9 in this class. I only have 7 of you. So someone is asking for attendance. All of you are here. So, okay, in that case, next Wednesday, we'll do online class like what we have today as well. And so if let's say you happens to be in campus, right, you can use our classroom so that you have a venue to do the online class. So tomorrow will be online tutorial. Next week, Wednesday, we are going to do online lecture. And then Thursday, we are going to do online tutorial for fire and explosion. So that will cover week 9 and week 10. Week 11, we're going to talk about risk assessment. And then we're going to do our tutorial on Thursday as well. And week 12, we can actually, that's where you submit your assignment, okay? And then week 12, you still have class and tutorial. And week 13, we are going to use the tutorial slot to do your presentation, okay? So it will be a physical presentation. So week 13's tutorial class on Wednesday is your presentations for your case study. Then week 13 lecture class is online. We are going to talk about the remaining chapters on code and standards because I really swapped that classes to later week because those are again theories. There's no tutorial classes for those. Then week 14, we're going to do revisions to prepare you for your exam. I think that's lay out what we are going to do for the next few weeks. Is that all right? So this week and next week, all our classes will be online. Yeah, since many of you said you're okay with online. So, but week 12, we have our lecture class physically because that one's we are going to draw some things and we are going to do some activities in the class. We can do that. And then week 13 will be again physical class for your physical presentations. And week 14, we can do physical class for the revision. Okay. So any questions regarding today's chapter? If no, then I'll see you all tomorrow then. Okay, thank you. See ya tomorrow. Same link, yeah? Thank you and have a nice day.